This lecture today is about stochastic and data-driven optimization, and so there's going to be a little bit of theory and fundamentals, nothing too advanced, and then we're going to talk about some applications in power systems. Okay, yes. Okay, so as a motivation, most of you have worked with optimization. Has anybody not worked with optimization before at all? No. So you've also probably worked on optimization under uncertainty. Raise your hand if somebody is not. Okay, so you haven't worked on optimization with uncertainty. Ah, okay. Okay. Yeah. So basically, we're going to look at a class of problems to solve decision-making problems when we have some uncertainty on the inputs of our problem. So we're going to look at a simple case of what we call stochastic optimization problems, in which the input parameters are uncertain and follow a known distribution, and for which we have only one stage of decision variables, which means that we have one shot to make our decisions before we observe the value of the unknown input parameters. So there is no recourse or second chance to change our decisions. And in this optimization problem, we're trying to maximize the expected profit over the realization of our uncertain parameters or minimize the expected loss. So I've written a standard formulation for this type of optimization problem where we minimize over X, which is in some feasibility set. You can see the feasibility set doesn't depend on the uncertainty, so X is always feasible regardless of the value of the uncertain input parameters. So over this set of X, we're minimizing the expecting loss function, which is a function of our decision variables and our uncertain input parameters. So this is a very standard formulation and a simple case of stochastic optimization problems. No, the other way around. Yeah. So one very classic example of a stochastic optimization problem is the news vendor problem. So I think it appeared for the first time in the literature in 1888 in a paper about the mathematical theory of banking. It wasn't related to news vendors, but to basically how much reserves banks should have so that they can handle cash withdrawal. So if you had an ATM and you didn't know how much people want to withdraw, how much money should you put in the ATM? But it's the same class of problem as the news vendor problem. So let's look at specifically the news vendor problem because it gets its name from news vendors. So what is the problem of a news vendor? So the news vendor in the morning needs to go to a warehouse and buy a stack of newspaper. So he can buy in the morning for $3 a newspaper from the warehouse and has to decide how much he wants to buy. Then during the day, it goes from person to person and sell them one by one. He can sell them at $5, so he can make a profit of $2 per newspaper that it sells. But it doesn't know how many people are going to want newspapers during the day. So that's its uncertainty, right? And it has to decide in the morning how many to buy and carry around. So if it doesn't manage to sell all its newspapers, then it can also transfer them back to the warehouse at a loss. So it can sell them back for $2, so it loses $1 per journal, per newspaper that it didn't manage to sell. So we have a marginal loss if we buy too many newspapers in the morning. That's $2 per newspaper. And we also have a marginal loss if we have extra newspapers of $1 because we sell them back for less than when we bought them. So the question for this news vendor is how many newspapers should he buy in the morning to maximize its profit or minimize its loss, right? this is very classical problem, but it has many applications. There's a lot of problems that we solve in real life and in power system that have exactly the same structure. And this structure, so to qualify to be a news vendor type of problem, is to have a one-shot possibility at deciding on the quantity of interest. So one-stage decision. We have uncertain outcomes. Here was the demand for newspapers. We also have known marginal profits or losses. And our goal is to maximize an expected profit. So this is pretty generic, and that covers a lot of problems. So can you think of any problem of optimization in power system that could fit into this framework of a news vendor problem? Yes, so how much reserve to buy if you're a TSO? Yeah. So yes, that's a very good example. So in this case, you have to decide in advance the reserve. You don't know how much you're going to need, how much you're going to need to activate, right? You know the marginal cost of buying that reserve, yes. And you're trying to minimize the cost of operating the system. So yeah, that's a very good example. Another example that I chose, we're going to look at this one instead, is a wind producer that wants to sell electricity in the day-ahead market, right? So imagine I'm a wind producer. I'm a fairly small wind producer, and I want to trade in the day-ahead market. We look at the case of Denmark, for example, because market rules change a little bit from country to country. So I want to trade wind in the day ahead. I'm also balance responsible, so whatever imbalance I have in real time. So if what I end up producing doesn't match what I sell, I have to settle in real-time market. And I have available some inputs, so I can have collected maybe some historical data on the electricity prices, on my wind production. And I also have maybe mechanisms to forecast some of the relevant inputs that I need. So what does this wind producer do then? What is its problem exactly? So it wants to participate in the day-ahead market. And so its profit, the first part of its profit is how much money it makes by selling electricity in the day-ahead market at the day-ahead price. So the quantity that it sells in the day-ahead market is the decision variable, and it's called X. I don't know. So that's the first part of its profits. Then once it's participated in the day-ahead market, it realizes how much wind it actually produces, and it has to settle imbalances. So if it has surplus, so if there is more wind production than what it has sold, so the realized wind is called W here. So if W is greater than X, then it has to sell this surplus. And the way it works in Denmark is with some, so two-price, at least it's worked like this for a long time, is a two-price settlement. So the price at which it can sell the surplus energy that it has depends also on the system imbalance. So if the system imbalance is positive, means that the system has too much power already, and it wants generators to reduce their production. And I have too much production, so I want to sell to the balancing market. Then I can sell it at the balancing price, and in this case, the balancing price is going to be lower than the day-ahead price. And then if, on the other hand, the system has negative imbalance, it means that it needs the producers to increase their generation. In this case, the balancing price would be higher than the day-ahead price because we need extra energy for the system perspective. But with the double price system, instead of being able to sell at this high balancing price, I can only sell at the day-ahead price, my surplus energy. So in any case, I can never sell in real time or in balancing market for more than the day-ahead price. So somehow, I always have some kind of penalty if I sell surplus compared to if I had sold in the day-ahead market. And then there's a similar mechanism this time if I have a deficit of wind, so if I have less wind production than what I had anticipated, then I need to pay for this deficit, and I need to pay at downward price, which will always be higher than the day-ahead price. So whatever I had sold in the day-ahead market, then I'm going to have to pay for what I had sold too much of, but at a higher price than what I had sold. So in both cases, whether I have surplus or deficit, I always incur some marginal loss for not being exact on my forecast. So in this case, the marginal loss, if I have extra wind, we can denote it phi with an up arrow because I need to increase my production. And it's the difference between the day-ahead price and the upward price. And it's always positive. And the same way we can define a marginal loss if we have a deficit of wind production, phi with a down arrow, which is always also positive. Is this a news vendor problem? Does it check all the boxes? So we have a one-shot decision, how much we're going to sell in the day-ahead market. We have uncertainty on the outcome, so how much wind generation we're actually going to get. We assume that we know those marginal losses, and our goal is to maximize our expected profit. So this ticks all the boxes of a news vendor problem. So how can we formulate then and solve this problem? So I can, so the issue now is that actually I have those marginal losses that I might not know, but I can actually reformulate this problem to get rid of those uncertain parameters. So right now, my profit is, so my day-ahead price times production, plus the surplus that I sell. Here I put a plus, meaning that this is equal to 0 when this is negative, and it's equal to this quantity when it's positive. So minus then what I have to pay for my deficit. Again, if I have any deficit, otherwise this is equal to 0. So this is my profit. Now I can reformulate this to make appear those marginal losses instead by adding and subtracting lambda day ahead times this quantity. So now I have lambda up minus lambda day ahead times W minus X plus. And now I need to add lambda day ahead W. This is not very visible, right? It's getting worse and worse. Yeah, no, definitely not. Same with the downward penalty. This is just some manipulation of the objective. So I have here minus lambda day ahead times W, not times, sorry, this is X minus W, X minus W plus. Okay, so now this is minus the upward penalty. This is minus the downward penalty. And now let's look at this. So we have here lambda day ahead times this quantity, which is equal to 0 if we have deficit, and W minus X if we have surplus. And here we have lambda day ahead also times this quantity, which is the other way around. So one of those quantities is always equal to 0, and the other one is equal to x minus w or w minus x. So this actually simplifies these two equations to, so these two parts, they simplify to just lambda day ahead times w minus x. And here, lambda day ahead minus x, lambda day ahead x, those simplify. So now we just have a profit that is lambda day ahead times w. This is fixed because none of this is a decision variable. And then minus our marginal losses, right? Yes, right. So this is the profit that we have. But so far, we still have those penalties that depend on the balancing prices, which we don't know yet. So I can simplify this to basically make appear the ratio of those. So if I define, if I just divide this by the sum of those two penalties, right? So one of those two penalties is always equal to 0, and the other one is different than 0. So these are two positive quantities. So let's say I call this u. Then this is 1 minus u, right? So now I've just changed variables to have this u. And what is this u equal to, right? There's two cases. Either the penalty for upward is equal to 0. Then in this case, u is equal to 0. And 1 minus u is equal to 1. Or the penalty for upward is positive. Then that means the penalty for downward is equal to 0. And then this simplifies to just the ratio of penalty upward divided by penalty upward. So u is equal to 1 or to 0. Those are the only, those are the two values that u can take, actually. So it's a binary variable that is unknown. So we've simplified all the uncertainty to just now a, yes. So here I called it S. Yeah, so we've simplified this problem to just two sources of uncertainty, so the wind and U or S, which is a binary that's distributed as a Bernoulli with a chance of success tau that represents the ratio or the asymmetry between upward and downward penalties. So if we can, yeah. Yeah, I can, but this is constant, so when I optimize, I don't need to take it into account. It's just a constant that adds up. So I can maximize it. P is the same as maximizing P minus this. Yeah, but okay, I removed this first, so I'm maximizing this. So first I remove it because it's constant, and then I divide by those two terms. And this is always positive. Yeah. So in the end, I can just minimize this slightly modified loss constant, and I'll get similar, I get the same results. And the benefit is that now I've reduced quite significantly the amount of of uncertainty that I have in my problem. So when I need to model those sources of uncertainty to actually solve the problem, that's going to help me later. But we still have two sources of uncertainty to model: the wind, which is a continuous, so the wind production, which is going to be a continuous random variable, and also a discrete random variable. So for the discrete variables, it's easier to model because it has a discrete set. So calculating an expectation over this can be calculated quite easily as a sum. But for continuous variables, the expectation is going to be an integral over the support of this random variable. So in the general case, computing these integrals directly can be quite challenging and computationally challenging and can become intractable. So we can't usually solve this optimization problem as is and compute those integrals in the general case. So we need to go around this problem of tractability. So I said that when you have a discrete random variable, it's easier because this integral to calculate the expected value is a sum. So the idea is of stochastic programming and scenario-based stochastic programming is when we have a continuous random variable to go back to the case where we have a discrete one and try to approximate the original problem by a simpler one. So this is basically a sample average approximation. If we assume that we know the distribution of the continuous random variable, we can use this probability distribution to generate a very large sample of scenarios that are distributed according to this distribution. Once we've done this, then we can replace as input of the stochastic optimization problem the original probability distribution by the empirical distribution of the sample that we have generated. And by doing that, then we can simplify this exponential in the objective function, this expected value or this integral in the objective function by a simple sum. So now we have just a linear optimization problem, which helps a lot with tractability and solving this for large-scale problems. So some of the motivation why it is valid to do this and why it's a good idea to do this sample average approximation is that, well, first of all, the empirical distribution of the sample that we generate is an approximation of the target distribution and will converge to it when we have an infinite number of samples. And the second one is that the sample average is an unbiased estimator of the expected value of our continuous random distribution. So their expectations are the same, and actually they also converge with a certain rate that you can calculate when the size of the sample increases. Yeah.
I missed the meaning of a few terms.
Oh,
for example,
sorry.
what is the S and the W in the previous equation? Because I think that
X is the decision variable, yes.
But
S? Yes. Yeah. So I mentioned that I made a typo. S is U here. It's when I derived, I wrote it U, but I made a typo in here and called it S. So it's a random variable that is binary and that I defined like this. Yeah. And W is the wind realization, so how much wind production is available, which is an uncertain quantity at the time when we're participating in the day-ahead markets. So were that the only ones that I went over too quickly on? Okay, yeah. Sorry. Yeah, so yeah, just like as a little background or very quick yeah, background for those of you who maybe aren't familiar with it or are wondering, so how do we actually generate a large sample from a distribution of interest? So for some complicated distribution, even if we know it, it might not be that easy, but we can use Monte Carlo type of simulation. So if we can sample from a uniform distribution, so we might not be able to sample from any distribution, even if we know it, for some complicated distribution. So let's assume this is a cumulative distribution function that I know, but yeah. So I want to sample from this, but I don't know how to do it directly. Then I can generate some random samples that are distributed as a uniform distribution between 0 and 1. And then I transform those by taking the inverse of the cumulative distribution. And then when I invert those, the samples that I get are distributed according to the cumulative distribution of interest. So there's a lot of more advanced methods, but generally that's how it works. So even from pretty complicated distribution, I can sample an arbitrarily large number of samples. So I can get a pretty good sample average approximation of some pretty complicated distribution. That's under the assumption that I know those distributions. So
binary, right?
U is binary, but in this case, the wind, for example, isn't. So the wind generation isn't binary.
No, yeah.
So if it's a binary, then that's easier. But for continuous variables.
No, yeah. No. I thought that you were drawing samples from
yes, from a uniform distribution. That's why I called it U. Yeah, it's misleading. Not U. V.
But that U is
Sorry.
not the binary variable.
No. Yeah, you're right. There's just some V. Yeah. You're right. Yeah. Bad notation. Yeah. So we can use this. It's a good tool. It works pretty well, even for some complicated distribution, under the assumption that we know those distributions that we want to sample from. The other challenge, which isn't just that it's difficult to compute those integrals for complicated probability distribution and to solve the standard stochastic optimization problem, it's that the true probability distribution of my input parameters, it cannot be observed in general. It cannot be known perfectly, right? If I have an uncertain parameter, this probability distribution that I assume it takes is just a model that I am constructing to represent its uncertainty, but I never observe it directly. What I observe is some samples drawn from this distribution, but the true underlying distribution I am just trying to estimate, basically, when I'm constructing a model of it. And there's always some estimation error. So assuming that we perfectly know this distribution is also a big assumption. So what we do have is some limited observation of samples drawn from this distribution, and maybe some expert knowledge also from which we can draw to build this probability distribution, right? Maybe we know about the support of this distribution. So if I'm wind producer, for example, the support of my wind production is going to be between 0 and my maximum capacity, right? So that's also some expert knowledge that I can use. So what I'm trying to do when I'm trying to model then this probability distribution that my random variable follows is typically, if I look at the historical data, I have some samples, and I'm trying to find a probability distribution that fits this historical data, so that explains this historical data, right? Based on the amount of data that I have, the type of data that I have, and how the unanimity of this data, then there might be more than one probability distribution that fits or that could explain this data with some pretty good confidence level, right? So especially if I don't have a lot of data points, then there might be a family, a lot of distribution that could explain my observations, right? And so in real life, this kind of problem, we face it often, and it's what we call ambiguity, right? So anytime we observe something and it could be interpreted in more than one way, right? We face some ambiguity on this object. So for example, if you look at this image and I ask you, what does it represent? Then I would get some different answers, and whoever tells me it's a duck is probably going to be fairly confident that it is a duck. Whoever tells me it's a rabbit is also going to be very convinced that it is a rabbit, right? And both of those are good explanation or good, good interpretation of that image. They're valid, and if you hear a sentence also that could be ambiguous, like I'm a huge metal fan, that could mean many things, right? And you wouldn't be wrong if you interpreted it one way or the other, unless you have some contextual information about me, and then you know I'm not an appliance, but then that's out of the scope. But so that's some type of ambiguity, right? So since my probability distribution that I'm trying to construct is a model that explains my data, it's also an interpretation, you could say, of this data. So when there could be many probability distribution that would fit the data that I'm observing, then I say I have distributional ambiguity. So I have ambiguity on the true probability distribution. And this is an issue in stochastic programming, right? So how would that actually impact the solutions of an optimization problem? Let's say let's take a small example, right? Let's see how ambiguity on the inputs and estimation error on the inputs can impact the output of my optimization problem, right? So we can take a small example. So I have a set of objects in front of me, and I can only pick 4 to put in my cart. And I want to maximize, I guess, the value that is in my shopping cart. So we have these 8 objects, right? A ring, books, a watch, a phone, a statue, a bike, violin, and a football table. And those are the true value of those items, right? So if I look at this, which 4 items should I pick if I want to maximize the value? Yes, so I pick a statue, bike, violin, football table. It's not a trick question. That is, like, if I observe this, that's what I should pick. But, so we said, yeah, this would be then the optimal mean value, average value of the items that I have in my cart, right? And that's the best I can do. But we said I'm not observing this value. So there might be some estimation error when I observe these values, right? So even if I assume that the error that I make on those observations is not biased. So for some of them, I'm going to overestimate how much they cost. Some of them, I'm going to underestimate their value. Even if we assume that those errors cancel out, so in expectation, I'm actually not making any error on my estimation of the value of the object, right? But how do you think doing this would affect my solutions? So let's say I'm overestimating half of them, underestimating some of them. Does that mean that the value of my solution, then would I overestimate, underestimate the value of the items that I have in my cart? Do you have some intuition on what would happen? Yeah?
I think you'll overestimate.
Yes.
Because the items that you pick are the ones that you overestimate.
Yeah. So that's true. You're more likely to pick the ones that you're overestimating. Exactly. So yeah, let's, for example, some pretty big error, but they all cancel out. So I have some I overestimate, some I underestimate. Then if I observe this, then I would pick, if I try to pick the 4 most valuables, then I would pick the violin, the statue, the watch, and the football table, right? And 3 out of 4 of those are items that I have overestimated. So you're more likely to pick then objects that you have overestimated the value of, so you've been optimistic about them. So then what you think you will realize as a mean value is also optimistic. So you think you have more than what those objects are worth, and also more than even the optimal mean value that you can achieve, right? So then, after this optimization, when you actually observe how much those, the actual value, you realize a value that is not only lower than what you estimated, but also lower than the optimal you could do, and you have some disappointment, right? So there's some post-optimization disappointment. Even if you have unbiased inputs, you have biases in your outputs, likely. And not in a good way, because you're being too optimistic, so you're going to be disappointed with your actual outcomes. So basically what I'm trying to say is that even if I'm doing some pretty good approximation and estimation of the underlying probability distribution, I could have some pretty big impact on the outputs and the solution of my optimization problem. So how can we deal with that, right? What time is it?
10 to 3.
Okay, we have time, sorry. 3:30, we can have a break, if that makes sense. No? What? How many breaks do you Okay, then we can have a break. Wait, is it 10 to 3 or 10 past 3?
10 to 3.
10 to 3. Okay, then in 10. We didn't start at 2 also. So.
So now is a good time?
Sure, yeah. Yeah. No, it...
No, you wanted to do it in 10 minutes.
Yeah, let's just a couple more slides.
Yeah.
So we want to use, the proposal is to use an alternative approach, right? Not relying on those estimates of my, of the underlying uncertainty, but directly using the data that I am observing and build a mechanism, a data-driven mechanism that gives me a candidate decision as a function of those input parameters, and also that allows me to derive some certificate of the quality of those decisions, right? So typically, when I have a, I have some observations, right? I can use some of them for training, for making my decision, and then some for validating my decisions, right? So in machine learning, you usually split your data set between your training and testing data. So that's the similar idea, right? So I want to use my training data then to find candidate decisions, and then I want to derive certificates of the quality of those decisions on my testing data. So what is actually this certificate? Before we look at the different approaches for solving this, what does this certificate represent? What is this certificate? So I'm making a decision. That's a function of my training data. And I want to evaluate it on the testing data. So you could say out of sample. I want to evaluate it. So on the testing data, I can calculate the expected loss, my expected objective over the testing data for this fixed decision, right? And as the number of samples in my testing data set increases, this will converge to what we can call the out-of-sample performance, which is the expectation of my loss function with respect to this distribution of the testing data, and for this fixed decision, which has been taken based on my training data set, right? So we know that this out-of-sample performance, this out-of-sample performance, which is the expectation of my loss function for a fixed decision, is greater than the optimal loss, right? Which I don't know, but I know that it is greater than the optimal loss. I cannot do better than the optimal, the smallest loss that I can achieve. So that we know. But the certificate that we want to derive is an upper bound for this out-of-sample performance. So we would like to find some upper bound for this with some level of certainty, right? Specifically, there's a certain number of desired properties that we want our data-driven mechanism to satisfy. So the first one is a finite sample guarantee. So I would like to be able to say that for a certain size of my training data set, I can find an upper bound for my out-of-sample performance with that will be satisfied with a high probability. So I can play on those parameters, beta and n and j, to find some guarantees that are satisfied. I would also like to know what I call asymptotic guarantee, which means that if I had an infinite amount of training data, I would want that the solutions that I'm making are actually converging toward the optimal solution, right? If I have an infinite amount of sample, then it's as if I had the true distribution. So I would make the optimal decision. So both the solutions, but also the objective value should converge towards the optimal one with the probability one. And the last desired property, which is important, if not the most important one, I guess, is computational tractability, because it's very nice to have a method that has those nice guarantees, but if I cannot solve it, then it's not very useful. So I would like to be able to solve this problem, even for large scale problems, in a reasonable amount of time. So those are the three types of properties that ideally I would want my problem to satisfy. So then we can take a break, and then later we can talk about different ways to, different mechanism, data-driven mechanism to, that we can derive and what their properties are.